Welcome to lecture 30. In this lecture we're going to discuss something that is very key to taking our understanding of classical mechanics further, and that is the force, the relationship between force and potential energy. And analyzing that will include discussing energy graphs, where we're plotting potential energy of a system against some kind of position variable, and this will allow us to get a very intuitive understanding of how the system behaves. So let's get started. I want to start by reminding ourselves what potential energy is. So potential energy was defined, well, it wasn't ever really defined. What we defined was a change in potential energy. Let me write delta potential energy. The change in potential energy, that was the work done by the force associated with the potential energy. So if this gravitational potential energy, this was the work done by gravity as I move from one point to another. Actually not quite true, I should put a minus sign here. Why is that? Well, let's take the example of gravity. So for example, this would be mg times the change in height. When an object moves from somewhere up to somewhere down. And if I move from up to down, then I'm losing potential energy, but gravity is doing positive work. Right, write this down. If I lose potential energy, the gravitational potential energy, well, gravity or the weight does positive work. I think it's easiest seen using that kind of example. Right. Now, of course, we don't have to use the concept of work when we can use potential energy. It's a lot nicer in our calculations, but that is how it was defined. Right? And only when the work done does not depend on the path, then there was potential energy to speak of in the first place. Okay, so I'm now going to call the potential energy U. It's just something you often see, and so you get used to it. I'm going to do it too. So my potential energy is going to be denoted by the big letter U. Instead of writing PE or something like that, or writing it out, I'm going to call it U. Again, that is just a convention. So let's put the pieces together then. What's the work done? That's the force times the displacement, of course in the right direction. Remember, to do that, I have this convenient dot product notation, but you can also write it out as in components, fx times delta x plus fy times delta y, and so on. But if you can't remember this notation, you haven't done the dot product, go back to the lecture in which I introduced the notion of work. So this is the work done, and that is equal to the change in U. Oh, I forgot the minus sign again, and put it here, right? This is the work done, change in potential energy. I can easily rearrange that, find that the force is minus the change in potential energy. Let me actually go to one dimension right now, just to keep it conceptually a bit simpler. Can generalize again later. After the force is minus the change in U divided by change in the position. So what does this mean? It's saying the force is minus the slope of the potential energy with respect to position. So I'm just going to call it the negative slope. Of potential energy with respect to position. We're just manipulating the ideas we've already developed. Now, just for completeness, I should of course add that sometimes this is not, like the force isn't constant, the potential energy, the slope changes from one place to another. So in more generally, I should write this as a derivative, namely that the force is minus du dx. And if you want to take your classical mechanics further, this is going to be a very important relationship. Of course, again, we could justify this using the fact that really we had that, well, the change in potential energy, or minus it, is the work which I could write as an integral of f, which depends on position, dot dx. This is kind of the more formal justification for the general case where the force doesn't change. But I think right now this relationship is just sort of more intuitive to get to, right? We don't have to worry about calculus theorems. So if you feel comfortable thinking about those, you definitely should. Okay. Of course, the integral is taken from the starting position. Let's call it x initial to x final. You can think about what that means and what we're doing there. Let's do some quick examples using this sort of relationship, or maybe even this one here. So example 1. Gravity, the weight. So what's the potential energy? U grav equals, so potential energy of gravity, subscript grav, is mg times the vertical position. Let's call it y. Call it the height, h, doesn't matter. Right. So that implies that so the y-axis points this way. That implies that the force of gravity is, well, it is minus the derivative, the slope, if you like, of this with respect to y. Take the derivative of this, those are constants, so it's linear in y, it's minus mg, and indeed I could have done a delta u over delta y, and it would have ended up with mg just the same. So it's just the weight, right? The thing you know and love, it's minus because if y is up, the weight acts down. Let's do another example. Let's take our example 2, the spring, or elastic potential energy. So for a spring, we have that the potential energy is 1/2 k, and then the stretch or compression squared. So I call this x. Let me draw it quickly. If I have a spring, and maybe this is how long the spring wants to be. There's going to be some mass at the end. Then this is my x-axis. Here 0. And if I squish it a bit or I stretch it a bit, well, that position is what's going to get squared. Right? So it contains energy if it's squished or energy if it's stretched. That makes sense. Well, what are we going to get if we try to find the force? So I need to take the derivative here because the force is not constant. Right? I can't easily take delta u over delta x. I could if I make the delta x very small, but that's just equivalent to just taking the derivative in the first place. So minus du spring dx. I take the derivative of this, so 2x goes, sorry, x squared goes to 2x. When I end up, the minus sign comes from here, minus kx, and that makes sense, right? K, how many newtons per meter, multiply that by the number of meters the spring is stretched or squished. When I get back the force, minus sign, why is there minus sign? Well, if the mass is in the positive x over here, the force is left, the spring pulls back. The mass is in the negative position here, to the left of 0, while the spring is compressed, so it pushes in the forward direction. It always pushes in the opposite direction of the displacement, hence the minus sign. That's another example. A force we haven't really talked about before. Let's go with electrostatic forces. That's something you'll learn in a future course in more detail, but we can just take the example here. The potential energy of, say, 2 charged particles. So maybe it could be 2 electrons, or a proton and an electron. Could be some macroscopic object that's been charged up. Maybe you've been, rubbing it with a piece of cloth or something like that. right? Or a balloon that you've been rubbing against the carpet. Well, if those objects are essentially point masses, so you can draw it like this, right? There's a charge, so charge Q1, charge Q2, this is electric charge. But if you don't quite know what it means, that's fine. We're just going to try to do a mathematical example. Right? Two particles, and there's some kind of electrostatic force between them. Well, I can just tell you right now, the potential energy is given by Q1, Q2. You multiply how much these are charged up. What does that mean? What kind of how many electrons are missing or extra here and here? Then I divide it by a constant that I write as 4 pi epsilon naught. Doesn't matter what we mean by it. And then R, and R is the separation between them. I'm just telling you this without proof, right? I'm just stating it. Look, this is how the nature works, how the force between or like the potential energy between two charged objects, what it looks like. I'm just going to take as an example, because then I can find the force of the electrostatic force between them. It's minus du. Now, what am I differentiating it with? Well, what's changing is the position. The position here is the separation r. So what does this make? Well, this is just a 1 over r. So we're going to get Q1, Q2 divided by 4 pi epsilon naught r squared. Notice the minus sign has gone away because by differentiating 1 over r, I introduced a new minus sign. This is the electrostatic force. Now, if both charges are positive, charges can be positive or negative. Those are both positive, and we're going to get a positive force, meaning towards increasing r. If one is negative, one is positive, that means this would be a negative number. So that means the force is towards decreasing r being our position variable. As an example you hadn't seen before, but you're going to meet again later if you stick with doing physics. So what it tells you is that if I hand you a potential energy function, there it is, I'm telling you, this is the potential energy you're going to need for this particular system, two small particles, whatever, right? That is all the information you need to figure out what the force is like between them for any kind of constellation, any kind of configuration that the system might be in. So stated this in this very sort of abstract way. The system is in some configuration that's described by some position variables. Well, if I tell you the potential energy function in terms of that position variable, you can figure out what the interaction between them looks like. And this actually generalizes to more than one dimension as well. I want to show this to you conceptually. So imagine you have a map, right? This is a map, and these are my contour lines. If you've ever been on a hike, you know how to read those. The contour lines are lines of constant height. So there's a mountain here, and I guess this is 100 meters, 200 meters, 300 meters, 400 meters, then this would be 500 meters. So the kind of the peak is here, and then if I go around the mountain at a constant altitude without going up or down, this would be the line I'll be going along. Of course, I could be drawing lines at 250, 350, or at every meter, just become a bit crowded. Right, and there's a second kind of lower peak right here. Now, this is a map not just of altitude, but of gravitational potential energy. Right, so you think it's a map that's showing you the height, but actually it's showing you the gravitational potential energy of an object, such as a hiker, moving from one place to another. Why is that? Well, because gravitational potential energy is just a constant mg times the height. So it'd be 200 times the weight, 300 times the weight, 400 times the weight. That would be your potential energy if you hike up here and you sort of hike up the hill, something like this. Okay? So this is a map of potential energy. And now I can ask, well, what would be the force on, say, a marble? Let's go I'm going away from the hiker. Let's pretend it's a marble. I'm going to put down on the hillside right here. Which way would it roll? If you can picture what this hill looks like, you'd realize the marble would of course go straight down the hill this way. If I put a marble over here, at this point, well, it wants to roll down the hill, right? And a lot of directions down the hill, but it goes straight down the hill. So because the lines are further apart here than they are over here, you can just look at it and be like, it's not as steep. So the downhill force isn't as big. And that's exactly right? The downhill direction, the downhill slope tells you the force. It worked in one dimension where we did it algebraically and using calculus a little bit. But it also works just graphically like this. If I can visualize the potential energy with a map like this, I can just by looking at the contour lines, I can say which way will the marble roll if I put it right here, and what will be its acceleration. Why? The downhill slope gives me the force. Of course, here the force, as you know from having studied systems going down a slope like boxes and marbles and whatnot on a slope, is a combination of the weight that's straight down, like into the page, towards the center of the earth, and the normal force of the hill. But combined, right, I'm going to get acceleration as mg sine theta. Well, where the further apart, I'm having a lower slope, so the force is smaller. Where they're closer together, the force is bigger, and the force always points straight down the hill. It helps you visualize this in 3D. Right, like there's a mountain here, you put a marble on it, pretend there's no grass, it's just smooth rock, it'll roll in that direction, and so on. We'll come back to this kind of picture a lot more when you start studying electrostatics and you talk about electric potential and electric potential difference. So you'll want to come back to this video you're watching right now, maybe at that point. And I want to come back to a one-dimensional example where there's just one direction of position that's relevant, and I'm going to look at the spring again. What I want to do is I want to plot a graph of the potential energy of the spring against the position. Now the spring has a potential energy U, it's 1/2 kx squared, where x is the distance or displacement from the equilibrium being the sort of natural length that the spring wants to be at. So if I plot this, you can see it's a quadratic. That's going to look something like this. Right, it's a parabola. Now, how steep is it? Is it tighter? Is it broader? I haven't put any values here, but it just depends on the value of k. Right? If I have a higher value of k, I would have drawn it steeper on both sides, but the overall shape would have stayed the same. So this graph is my potential energy. And now we can right away see, using the principle we just derived, that the force is the negative slope, the downhill slope. We can see which way the force is going to be. If the position of the end of my spring, maybe there's a mass attached to the end of my spring, so let me maybe draw it. Right, there's a mass, right now it's in the middle. Now if the mass were to move to this position, so I'm pushing it to the left, then the force would be to the right. How can I see this from the graph? Well, if I put a little marble here, that's my intuition, then the force would be in this direction. If my spring is the mass, the end of my spring is slightly to the right, well, maybe I'm at this position here, there'll be a force to the left, but the force will be a lot smaller. Why is that? Well, if the spring is only stretched a little bit from here, this mass, let me write it on it, mass is moved over here. It gets pulled back, but not as strongly as it got pushed to the right if I move it all the way over here. From the graph I can see that too. Here the slope is fairly shallow still. If I stretch the spring all the way over here, right, now I can just look at my slope at this point, and it's pretty steep, downhill is left, and so I get a force like this. So these types of graphs, these potential energy graphs, they give you a very nice intuition. The intuition is, just pretend you put a marble here at the position that you're looking at, that you're considering. So if I put a marble here at x equals -5, doesn't matter what the exact value is, then the marble would start rolling to the right. And indeed, the force here is to the right. The force is not gravity. There's no real marble, but I think it's a good picture that shows you, well, look, if the mass at the end of the spring has been moved to here, there'll be a force on it to the right, and the strength of the force is essentially given by the slope. So that's the intuition, right? The minus sign, let's check that the minus sign makes sense that we had, because remember, F is minus the slope. Right? The slope of the U versus X graph. Well, here, what's the slope? At this point, the slope is negative. It's down the hill. The force is positive to the right in a positive X direction. Here, the slope is positive. Right, it's up the hill, positive slope, but the force is negative to the left. Yeah, that makes sense. That matches this minus sign right there. Okay. In this picture, is there a point where the force is 0? Well, I know from what my system is, it's a mass and a spring, that if I just let the spring sit there, not stretch it, not squish it, the mass is just happily sitting there. There's no net force on it. So this is my equilibrium point on the graph. This is right here in the middle. I can tell from the graph because the slope there is 0. So the slope is 0 right here. 0 slope, 0 force. The spring is not going to move if I just let the system sit there. Okay. So now let's take this a bit further. Let me just draw this again so I have some more space. So we're going to draw the same picture. Let's do a quick sketch. I'm going to draw my potential energy graph. Here we go. Should be symmetric left and right. Now, let's imagine I'm going to take my spring. There it is, and I'm going to squish it. Right, so now the 0 point is, of course, here. Could have drawn it more accurately a bit to the right. So I start my system in the middle, and I'm going to squish my spring. So I'm going to move the end of the spring from the midpoint to the left. So that means I've given my system, just by putting it there, some potential energy. How much? Well, I can just read it off like here. Say this is my starting point from where I'm going to let the system go. And when you come back at some later point to study oscillations in more detail, you'll be dealing with this graph a lot. But it doesn't mean we can't start looking at it right now, because it's a very nice example. Okay, so I put the system here. Now right here, I squish the spring by the distance represented by this displacement here. Right, this displacement, that is the motion of the mass. So my spring has been compressed by this distance. But it's not moving, I'm holding it in place, 0 kinetic energy. So that means the potential energy here is just my total energy. Right, because I just placed it over here. It has a certain amount of potential energy, but no kinetic energy. Well, assuming there's no friction or air resistance, that total energy is not going to change. So that means this line here is going to be the total energy throughout. What does that mean? That means if I let go, right, so I've been taking my spring, I've been squishing it by this distance, I hold it in place, and I let go. I can see, because the system is here, it's going to be force on it to the right, so it starts moving to the right. And it's going to speed up. How fast is it going to go? Well, let's say I want to ask about a system at this point, a bit closer to the center. Well, now it only has this much potential energy. Like this point here, because a read of what the potential energy is, just by reading it off on the axis. But if the total energy hasn't changed, that means the missing piece is kinetic energy. Right? Total energy hasn't changed, but the potential energy has dropped just because the object has moved. It means it must have gained kinetic energy. Of course, assuming there are no other forces acting that I have to take into account. Alright, and that then allows me to not only say, okay, which way is the force, but also how fast is the object going. And I can take it further. So let's look at some other examples to practice this intuition. Here's another example of a potential energy graph. Let's imagine the potential energy function looks like this. It's not a parabola, it's some more complicated shape. So I don't know what that is. I just made it up. It's some kind of mystery force, some new interaction. We've just discovered the potential energy looks like this. There's some position variable here. I haven't defined what the system is. We just work with it in the abstract now. And I give you this graph, and you can tell me a lot about how that interaction works. A mysterious force we're trying to explore here. Well, let's suppose I put my system in the position that is represented by the x value right here. So that means I'm giving it that much potential energy to start with. Now, if it doesn't have any kinetic energy, that is going to define the total energy. So, what's going to happen? Well, there's a force to the right. Right? So right here, there's a force to the right. How do I know that? The slope is down the hill like this. So if I put a marble here, it's going to roll to the right. The other thing I know is that this line here is going to define its total energy. So if I draw this line all the way across, what can I conclude? I can conclude that the marble is going to go over here. It's going to be very fast here because it has, well, this much kinetic energy. Right? When it is at that position. It's then going to slow down again. It rolls up a hill. Now, is it going to make it over the top here? Depends. Right? It looks almost like it has zero kinetic energy left. But let's say it has a tiny, tiny bit. It's going to get very slow. It's going to speed up again once it makes it over the top. It's going to go super fast here. Right? This is where it's going to be the fastest. Because it has the lowest amount of potential energy, so the most kinetic energy. And it's going to slow down again as it rolls up the hill, and whatever that physically means, I don't know, right? It means an increase in x from this point to this point. Well, the potential energy increases, so I know that the system's kinetic energy decreases, but once it reaches this point, it's going to stop. Like, it can't go any further. I know it has to turn around right here. Why do I know that? First write it down. Turnaround point. How do I know that? Well, because it has zero kinetic energy left. Because, again, all the energy is potential. Because at this point, at this position, x, x equals 8. Whatever, 8 nanometers, 8 kilometers, doesn't matter. Whatever, when the system is here, the total energy equals the potential energy, so it can't have any kinetic energy left. So it's going to stop right there. But not only that, it's going to stop, but the slope is down the hill, so it's going to start going backwards. Right? The force here is to the left because we're on a slope. And I can tell you all of these things, right, without knowing anything else except the potential energy graph. I can say, well, the object's going to move between here and here. It's going to oscillate back and forth. Another thing I could have done is that we could have started it a little bit lower. Maybe we could have started it right here. Right, so instead of starting the object here, I'm going to place it here. It's going to make a big difference because now, if this is my total energy, right, it's less. It's not going to make it over this first hill. It's going to go back and forth between here because this is its turnaround point. There's a lot of information I can get. This is a kind of a funny example. I made up this interaction. But is there some more realistic example? Yes. Let's have a look. Here's the example I want to look at, the bonding of oxygen molecules, O2. So this is the potential energy graph for the two oxygen atoms against the separation. So my variable here is the separation between the two, right? Here's one. That's not what they look like. But the distance between them, let's call it R. And this graph shows the potential energy against the separation. Now this is a nanometer, so 0.1 nanometers, that's a a tiny fraction of a meter, right? Nanometer 10 to the minus 9, so a billionth of a meter, well, a 10 billionth of a meter. This is very small. The energy here, the energy I've drawn this line here is 8 times 10 to the minus 19 joules, so tiny. Well, we're in the realm of atoms and molecules, so accordingly the quantities are extremely small. And this keeps going up, never quite crosses the line. So now you can imagine that if you're a little oxygen molecule and you have a little bit of energy, right, your total energy is down here, you're going to sort of bounce between those 2 points. So you're going to oscillate between here and at this point, small separation. The oxygen molecules are fairly close together, some kind of interaction between them. Over here, they're further apart, maybe like this, and they keep bouncing apart and together as the system goes between here and here. So R here isn't the X position of one of them, it's just the separation. The separation goes from short, maybe 0.05, to over here, which is maybe 0.2 nanometers, something like that. Now let's imagine you give this thing a shove. How would you do that with atoms? You might add some energy by shooting a photon at it. So that means I add some energy. Maybe now there's enough energy to be up to here, right? This amount of energy. So now the total energy would be here, and it would oscillate a lot more. Its minimum distance would now be here, a lot closer together than this, and be further apart too, but it still would just be going back and forth, because once it gets to here, okay, they're far apart, lots of potential energy, but they get pulled back together. I can tell because the slope of this graph is towards decreasing separation, right, to the left, towards smaller r. Now I'm going to give it an even bigger shove, and I'm going to shove it so much, I'm going to shoot a high energy photon at it, it gets absorbed, shoot it up to there. So what happens now? I'm above this line, and this line is the asymptote over here. So the potential energy over here never quite reaches it. It sort of flattens off. Well, now, if I start a system here, or even if it's down here, I can just add a lot of kinetic energy to make this total energy up here. Well, it's going to they get really close together, super close together, very small r, but then they move apart, and they keep moving apart. No matter how far I go, there's always some kinetic energy left, and so they'll never come back. The bond has been broken. So this energy that is needed, this total energy required to break the bond, to allow the separation to ever increase, is called the bonding energy, or the bond energy. And so in this case, for this kind of graph, we can differentiate between what's called bound states and free states. Alright, so maybe you can relate it to some other things you've learned in chemistry. Thanks for watching, and I'll see you in the next lecture.